And share screen. Share. Okay, can you see the slides? Yes?
Yes, we can see the slides.
Okay, great. Very good. Let me see participants. I don't know why it's not allowing people to get into the lecture right away, so I have to admit people. Let's hope this works. Okay, so today we're going to talk about a new topic, which is functional dependencies, and then next week we'll talk about normalization. It's something to do with design, database design. So we'll go back to the design. Remember, the first thing we talked about when we started the course was the conceptual modeling using the entity relationship model. Yeah, and you created one for your project. And that was to kind of say, okay, what are the entities and relationships and attributes and constraints that hold on your database? Then we converted this to the logical modeling using the relational model because we're working with relational database management systems like MySQL. Yeah, so this is how the relational schema looks like. So it's a set of tables with some attributes, domains for these attributes, and foreign keys and primary keys. Okay. Now, in practice or in reality, sometimes you don't have. You get into a project. So let's say you're hired in a company and you're the admin for the database. They ask you to be an admin for a database system that they already have. Sometimes people don't follow the guidelines for designing the database that we've talked about in the beginning of the course. So you kind of have a database that is already in production, and you want to evaluate this database. Is it a good database, well designed or not? Yeah. So that's the idea. So given a relational database that is already in production, can you decide whether it's a good or well-designed database? Okay. So you need to assess, right, how well the database is designed. 1 second. Admit more people. Okay. If there are issues to address, so you might want to restructure the database while preserving all the information stored in the database. So let's say you find out some problems with the database design. So the person who designed this database did not do a good job with the design. So you want to restructure the database a little bit, change the design a little bit so that it's a better database than the previous one, than the one you have. Issues particularly we're looking at are redundancy and anomalies. So these are the two main issues that you can find in a badly designed database. Another scenario or an example to motivate this is assume you're getting data from the web. So your job is to crawl a website and get the data in it and stored in a database. So sometimes, right, the way things are stored on web forms are not they're not very well designed. So basically, you end up having some redundancy and anomalies, as we've seen. Okay. So let's see an example. Here's a table, just one table, assume in an already existing database. So you have the ID, the primary key of the table, hence it's underlined. You have name, email, major, minimum credit, and GPA. If you look at this table, this is a poorly designed table. Why? Because it combines information from two different entities, the student entity and the major entity. So basically you have, for every major, you're storing with it the minimum credit. So repeating this information, you're saying the CS has 90 credits, mathematics has 120, English 80, CS again repeating 90. So with every student, you basically want to record their major, and you're repeating the information which is the minimum credit for a major. Yeah, so this is causes what we say anomalies. Yeah, it causes redundancy. So the information that the major CS requires a minimum of 90 credit is repeated more than once, basically with every student that is in this major, in the major CS. It causes update anomaly. So if we update the minimum credit of CS to 120, let's say we increase 1 year in the program of computer science, then you need to do it everywhere. Otherwise, your database will be inconsistent. So imagine that you decided to update the major CS, its minimum credit to 120. You have to make sure that you update this for every record in the database that belongs to this major. Yeah. Otherwise, you would have some students which are in CS and have minimum credit 90, where others have 120. Yeah. So you need to make sure that you update everything. So you're doing this update anomaly. Insert anomaly. We cannot store information about majors. So let's say I want to introduce a new major and it still doesn't have any students in it. I cannot insert this information in the given table. Why? Because the primary key of this table is student ID. So I can come here and say, let's introduce a major in literature or in biology, and right, this major has this number of credits, minimum credit. But then if you don't have any students for it, you wouldn't be able to insert this record in the table. So that's an insert anomaly. A delete anomaly, basically deleting, let's assume that you have only one student in the major English, because it's not a very popular major, let's say. Then if this student graduates and you want to delete her record, then you would end up losing the information about the English major, basically that it requires 80 credits. So that's a delete anomaly. So anomalies arise when you have these, the problem with redundancy, and we'll be able to quantify this, or be able to, given a table, say whether it suffers from redundancy or not, using some algorithmic checks. Okay, so what do we do with this table? How can we fix it? Any thoughts? We can, break it down into 2 tables. That's the right thing to do. You break it down into tables, one for student and one for major. So you say, okay, here's the student table, and every student I associate with it, its major, but then the major minimum credit information should be a separate table. And that's an example of what is called normalization. You take a table and you normalize it. You put it in a normal form. Yeah? These 2 tables are in a normal form right now, and you can say that now there is no redundancy and all of these anomalies have been taken care of. Yeah, of course, here major is a foreign key to the table major. Yeah, so this is a foreign key to this table. Okay, so again, we learn a set of algorithms to kind of do this automatically. So basically, of course, you cannot investigate every table. If you have a large database, let's say you're working in a bank and you have a large database with hundreds of tables and hundreds of attributes, it becomes very difficult to do this manually, to kind of go read check every table and check if there are any, these sort of redundancies or anomalies, and kind of fix them manually. Yeah, so we'll learn a systematic way of doing this using some algorithms known as normalization algorithms. Okay, so now once I have this, the table normalized into 2 tables, I can now easily update the minimum credits of any major without any problems, right? I only update it once because it appears only once. And then I can also insert a new major like, BA. I don't know what BA stands for, but let's say a major called BA, and I can set its minimum credit to another, even though there are no students in this major. This is not a problem because, right, this table major has its own key. Again, if I delete this record, right, the Salma Bahgat record, then I still have the information that English requires 80 credits. So this is, it takes care of all the anomalies we've discussed. Update, the insert, and the delete anomalies. So where does the redundancy come from, or the anomalies come from issue of dependencies. There are certain attributes in this table that depend on other attributes. Yeah. So basically, if you look at this, the major functionally determines minimum credit, or minimum credit is functionally dependent on major. Yeah, it's a very important concept in databases. It's used in data cleaning. It's used in, it has a lot of applications. It's a very important thing to know about databases. So the idea of functional dependencies. So what do I mean by minimum credit is functionally dependent on major? It means that the value of major determines the value of minimum credit. Yeah. So basically, that if I have to attribute major and minimum credit in this example, and minimum credit is functionally dependent on major, then I can look at all the values for major and see that if it agrees, right? So if I have two rows with the same value for major, they would have the same value for minimum credit. That's what it means that major functionally determines minimum credit. So if I look at this table, CS 90, 90. Math appears twice. I have 120, 120. Yeah. English appears right once, so it has, so it's, you know, there is no conflict. That's what it means. Something is functionally dependent on another. So when do we have problems? When there is an issue with the table and needs normalization is when you have a functional dependency such that, so X determines Y, let's say, and X is not a super key. What does it mean a super key? Remember super key, we talked about it at multiple occasions. It means that X is a set of attributes that are unique. Yeah, so if X is not a super key, this means that there could be several tuples with the same value of X in the table. Okay, so when do we have an issue? When we have two tuples have an equal value for X, they must have an equal value for Y. So there is a functional dependency between X and Y. So X determines Y, and X is not a super key, like in this example. Yeah, this is one functional dependency that causes issues, anomalies. Why? Because CS major is not a key, obviously, it's not a super key. So you have repeated values for major, and the function determines another attribute, which is minimum credit. Yeah, this means that this table suffers from anomalies or redundancy. Yeah. Okay. Good. So function dependencies are constraints over relationships between attributes. And a function dependency states that the set of attributes uniquely determines the value of another set of attributes. So it can hold between multiple attributes, yeah, by like a composite set of attributes on the left-hand side and a composite set of attributes on the right-hand side. Yeah, it's a generalization of the notion of keys. We'll see, we'll understand why in the next slide. So let's put it formally, let's define it formally. So what is functional dependency? So let's assume I have a relation R, which has a set of attributes. Yeah, so n attributes. And that alpha be a subset of these attributes. So it's a subset of R. So let's say, you know, a couple of attributes in R, beta, another couple of attributes in R. The function dependency alpha determines beta, or beta is functionally dependent on alpha, holds if you have for any two tuples, T1 and T2, if they agree on the value of alpha, so they have the same value of alpha, then they agree on the value of beta, right? That's what tells you this is, that alpha determines beta. Basically that they have the same values for alpha and beta, yeah? So they're the same. Alpha determines beta is called trivial if beta is, of course, a subset of alpha. Yeah? So this is a trivial functional dependency. So any attribute is functionally dependent on its superset. Yeah, let's see an example. So let's say we have a relation R, which has just two attributes, A and B. Neither A is unique, so neither A is a key, nor B is a key, obviously, because there are repeated values. So the primary key of this table is A, B together, the two columns, and that's why they are underlined. Okay, there's one non-trivial functional dependency in this table. Let's see if A determines B. Does A determine B? How can I tell? I look at the values of A, and whenever they agree, I check the value of B. Does it agree or not? So here I have A is 1, 1. And I have for B two different values, 4 and 5. So A determines B is not functionally, yes. B is not functionally dependent on A because I have 1, 1. Here's a counter example, 1, 1. And I have the values 4 and 5. So it's not the same for B. even though for 3, it's the same. Yeah, but at least I need just one example, counter example to make the functional dependency not hold. Okay, what about B determines A? Does B determine A? Yes, exactly. Yes, B determines A because if you look at it, right, for 1, that's unique, so we don't have to worry about it. 5, 1, that's also unique. 7. When B is equal to 7, you get that A is equal to 3 in both cases, right? And when B is equal to 9, that's only 1 row, so I don't have to worry about it. So only have to check the rows for which there are repeated values and check if the values, you know, in A are the same as the case in B. One sec. Yeah, then you're right. So this is just assume this is a temporary relation. You're right. Of course, A and B cannot be a primary key because you have 2 rows that have the same values. So I was mistaken. Yeah. So this underlining should be removed, and this is just assume it's a temporary result of a table. Okay. Good point, Mir. All right, so again, there's only one non-trivial functional dependency, that's B determines A. However, there are 5 trivial functional dependencies. A determines A, right? So attribute determines itself, the value of A determines the value of A. B determines B, AB determines A, AB determines B, and AB determines AB. Yeah, so these are called trivial functional dependencies because this is a subset of D. So what is on the right-hand side is a subset what is on the left-hand side. Yeah, here it's equal, here it's a subset, here it's a subset, here it's equal, and here it's equal. Yeah, so this is called trivial functional dependence. Any questions so far? Okay, good. So we'll understand a little bit more about functional dependencies and then we'll see how to basically characterize whether a table is poorly designed or suffers from redundancy and anomalies and how to fix that. Yeah. So basically, we have a set of axioms called Armstrong's axioms on functional dependencies. First one is reflexivity. So if beta is a subset of alpha, then alpha determines beta. That's what comes from trivial functional dependency. We said if beta is a subset of alpha, then alpha determines beta, like we did here. AB determines A. A is a subset of AB, then A is determined by AB. Okay? So that's the first one. Augmentation. If alpha determines beta, then gamma alpha determines gamma beta. So let's say I have a functional dependency which holds between 2 columns to make it simple, 2 columns, single columns. Then if I add, to the left-hand side, another column, gamma, or a set of columns, gamma, then gamma alpha would determine gamma, provided that alpha determines beta and gamma is the same set of attributes. Yeah, we'll see an example on this. So let's say I have another column C here, then I can say that given that B determines A, then CB determines CA. Yeah, it comes from this augmentation property. Transitivity tells you the following: if alpha determines beta and beta determines gamma, then alpha determines gamma. Yeah? So you have a transitive property on functional dependencies. Yeah, if alpha determines beta, and this beta determines another set of attributes gamma, then alpha determines gamma. Okay, there are additional derived rules from Armstrong's axioms. For example, the union, it tells you the following: if alpha determines beta holds and alpha determines gamma holds, then alpha determines beta gamma. Yeah, we can prove this using basically these set of properties. Yeah, so if you use this set of properties, you'll be able to prove these ones. So alpha determines beta and alpha determines gamma, then alpha determines beta gamma. Decomposition is the opposite of union. So if alpha determines beta gamma, then alpha determines beta and alpha determines gamma. So the counter opposite also holds. Yeah. So basically, this is the union, decomposition is the opposite. And pseudotransitivity tells you the following. Yeah, it's not very intuitive like the other ones, but we go through. So alpha determines beta, and beta gamma determines delta. So we have alpha determines beta, and beta, this beta associated with another attribute gamma or set of attribute gamma determines another attribute or set of attributes delta. Then alpha gamma determines delta. Yeah, so you can replace beta here with alpha. So alpha gamma determines delta. Yeah, so we'll use these rules together in a bit to kind of identify whether we have a problem in a table, was it fully designed or not, and to fix the table using these set of rules. Any questions about these rules? Okay, good. So we'll go back to keys, right? Being defined as defining keys as based on function dependencies, to relate keys to function dependencies, and then go on to identifying issues with statements. How do we use function dependencies to identify issues with statements? Okay, so K, a set of attributes, is a super key for a relation R if and only if K functionally determines all attributes of R. So given a set of attributes K, they are a key of the stable or a super key of the stable, meaning that they are unique, right? If they functionally determines every attribute in R. Okay. And K is a key, so not a super key, but a key. So a set of attributes is a key if they're minimal. Basically, if they determine every attribute in R, so functionally determines every attribute in R, then there exists no alpha such that alpha is a subset of K and alpha determines everything in R. So in other words, it's a key if there is no subset of it that is also a key, yeah, or a super key. So this is what it means that a set of attributes is a key versus a super key. So a super key means that it determines all the attributes in R. A key means it's minimal, yeah. So you cannot take any attribute out of it and you still have a key, yeah. So in other words, no other attributes in this set K, set of attributes K, is also a key. Okay. We'll move on to something else, which is closure, and then we'll do an exercise on all of this. Yeah, because this is will set up the process of characterization. So given a set of attributes, alpha, the closure of alpha under F, which is a set of functional dependencies denoted by alpha plus, is a set of all attributes that are functionally determined by alpha under F. What do I mean by this? Yeah, so it means the following. It means that, let's say I give you a table like this, and I give you a set of functional dependencies that hold on this table. Where do I get these functional dependencies? I can induce them from the data, but assume for now that they are given, yeah, that you are given this set of functional dependencies. Later on, we'll look into how do I determine whether a functional dependency hold, or how do I get, give me a table and I will give you all the functional dependencies that hold. Based on the data that is inside the table, I can deduce this. But let's assume I give you a relation and a set of functional dependencies, and I want to compute the closure of a set of attributes under these functional dependencies. What does this mean? It means basically all the attributes that functionally depend on the set of attributes AG in this example. So here's an algorithm to do this. What do? I start with all the attributes that in alpha. So I want to compute the closure of alpha under F. I put all the attributes in alpha because from trivial functional dependencies, they depend on each other. So if alpha determines alpha, basically. Yeah, so I add alpha to the result. And then while I have some changes in the result, I keep going over every functional dependency in F. So beta determines gamma. And, add, if beta is subset of the result, I add beta. Otherwise, right, I don't do that. Let's see an example. Yeah, this will be clear with an example. So let's say I have a relation which has 6 attributes, A, B, C, G, H, I. And I have this set of functional dependencies that hold on this table. So basically A determines B, A determines C, CG determines H, CG determines I, and B determines H. Let's compute the closure of AG. Yeah, so I want to get all the attributes that functionally depend on AG. So what is the first two? They are A and G. Yeah, because I have A and G determines A and determines G from the trivial functional dependency. Yeah, A is a subset of AG and G is a subset of AG. And now I go over these guys and add any attributes that depend on any of them. So I have B that depends on A. Yeah, so I add A. So I have A and G. I add B because A determines B, and I add C because A determines C. Okay, so these two attributes B and C become part of my closure. Yeah, meaning what? Meaning that AG determines also B and C because A determines B and A determines C. So this is using the rules that we looked at, the axioms that we looked at. Yeah, so you can, it's applying some of these axioms to get to these. Okay, so A, B, and C and G, because A determines C and A determines B. Now, next, what do I add? I have CG determines H, and CG determines I, and B determines H. So I can add basically H, right? Because B determines H, or CG determines H, and CG is part of, it's a subset of AG, BC. Okay, so I can use this functional dependency, CG determines H, to add H here, or B determines H, either of them. Okay, now what do I add next? I have also CG determines I, so I can add I. So A, B, now the closure of AG becomes A, B, C, G, H, I. Okay, so now I've managed to see that AG, right? I compute the closure of AG and it got me all the attributes in the table, A, B, C, G, H, I. What is the use of this closure thing? So why are we computing a closure of a set of attributes alpha under some functional dependencies? It can be used to determine whether alpha is a super key or a key. It can be used to determine if a functional dependency alpha determines beta holds. It can be used to compute what is called the minimum cover of a set of functional dependencies. Okay? So examining keys. How do I examine keys given the closure? So to test if alpha is a super key, all I have to do is compute the closure of alpha and check if it contains all the attributes of R. Yeah, this is really what I have to do. To check if alpha is a key, first make sure it's a super key. So make sure that it determines all attributes in the table. Then make sure that no subset of alpha is a super key. So basically, I check every subset of alpha and make sure that it's not a super key. Yeah, very systematic. So in our example here, we computed the closure of AG. Is AG a key? A super key, first of all, is a question to you. Is AG a super key? Even without looking at the data or looking at the table, I can tell from the closure of AG. Since it determines all the attributes in the table, then AG is a super key. Yeah, because AG determines A, B, C, G, H, and R. So all the attributes in the table. So then AG is a super key. How do I check if AG is a key? What do I need to do? I need to compute the closure of A. I'm gonna compute the closure of A. Can you see the markup? Yes? The notation? Okay. Okay, great. So what is in the closure of A? Can anybody tell me? First attribute is A, right? Because A determines itself. Okay, great. Then what do I add? Given the functional dependencies that I have B. A determines B, so I can add B as well. And I can add C. Correct? Okay. So I have B and I have C. I have also H because B determines H. So I can add H from a functional dependency. B determines H. Do I have anything else? No, right? So because I don't have G, and so I cannot add I. So this is closure of A. Yes, B, C, and H, right? Because B determines H. Okay. Now let's compute the closure of G. So what is the closure of G? You add G, of course. What else? Can I add anything else? Only G, exactly. I have only G, because there is no functional dependency here that tells me, right, G determines something else, some other attribute. So is A super key? How do I know? Does it determine all attributes in the table? No, it doesn't, right? It doesn't determine I. So basically, it doesn't determine G. So basically, this A is not a super key. So it's not a super key. Is G a super key? Obviously not, because it doesn't determine all attributes in table R. So then AG is definitely a key. Not only a super key, but a key. Because why? Because no subset of it is also a super key. So it's a minimal. Yeah, minimal key. You cannot take any attribute out of it and you still have a key. Okay? So this is how I examine whether something is a key. Any questions? Right. To determine whether a functional dependency holds, so alpha determines beta, all I have to do is just compute the closure of alpha and check if beta is in this closure. If beta is in this closure, then it holds. For example, let's say I have, again, my table R, and I have this set of functional dependencies. Right? We know that AG, since AG is A, B, C, J, H, I, that's the closure of AG, we computed it. Then what are the functional dependencies that hold? So AG determines what? AG determines A, AG determines B, AG determines C, AG determines H, and AG determines I. Yeah. When we computed the closure of let's say A, right? When we computed the closure of A, this gave me A, B, C, and H. So from this, I can deduce all these functional dependencies. A determines B, which I already have. A determines C, which I already have. I can also say A determines H, of course, right? Which I didn't have from before. So this functional dependency was not in the set. Yeah, A determines H. And how can I get this using the law? For instance, you can see that I can apply transitivity. A determines B and B determines H. From transitivity, I get that A determines H, right? So this is another way of figuring out whether this functional dependency, that A determines H. Questions on this? Okay, let's do another exercise, but I'll switch the meeting. I'll turn the meeting off and please join again, yeah? Because we're running out of time. To see you in a bit.